right, great. Thanks so much for having me here, and it's really an honor to be here at CppAfrica. I'll go ahead and share my screen here. You can see the presentation. And yeah, I want to thank everybody for joining. I know it's late for some folks, maybe early for others, depending on when you're watching. But again, thank you very much for spending your Saturday with me. Let's see, can everybody see my screen okay in the presentation?
Yes, I can see it.
Perfect, thank you. All right, so we'll go ahead and proceed here. So with today's presentation, we're going to be talking about computer systems. And I have a few different ways that I'm thinking about this presentation. One of the main is performance. And of course, C++ is a language that we use because we want performance. We want control over our actual hardware. So that's why it's a great language. But I also sort of have a working title of this. It's also a little bit of a back to basics talk on computer systems. So depending on your expertise, I think you'll find if you're a beginner, you'll be able to follow along. But if you're an expert, I think there's a few things that you'll also enjoy learning about or thinking about. So again, yeah, thank you again for hosting me here. We'll go ahead and dive into it. I have some of the source code, although there's not too much source code in a shared GitHub there. And again, today we're going to be talking about system stuff, as you've seen advertised. A little bit about me, if you're not familiar. My current role is as a teaching faculty at Yale University, where I teach courses on computer systems, game engines, graphics, and so on. And I've given a lot of talks in the C++, D programming language, computer graphics community. So that's where my professional and teaching experiences have been. And feel free to talk to me about anything as well regarding fun stuff that I enjoy from sports and basketball and these types of things as well. And of course, I've got a bunch of content on YouTube, so stuff that we're not going to cover in this presentation. I've got almost 1,000 videos at this point. A lot of it, over half of the content is C++ content. So hopefully you can find something that you enjoy there or otherwise engage with my community on C++ there. Okay, so I think that's enough of an introduction. We'll just go ahead and get into the presentation. And one of the things that I think is really amazing these days that maybe we underappreciate in some ways is just how impressive our computers are that sit in front of us. I mean, I've got my phone here, which I'm showing here, and it's got 4 processors on it. I can basically run, very impressive video games on it, take pictures, store full movies. It's just really incredible the types of computation we have even in our hands. And one of the domains, as I mentioned, since I've worked in video games and computer graphics in various capacities, I sort of use this as a benchmark just to see how far we've come in our journey. So if you can see early on what the computer graphics looked like in this game in 1999 to this same game in 2006 and then 2017, the graphics are getting better and better and more beautiful in many ways. And this is the same trend you'll see in other franchises. Maybe some of these games you folks will recognize, maybe not, but Tomb Raider. Again, you can see the computer graphics getting better and better as time goes on. And then we've got another game, Civilization. Again, from pixelated 2D graphics to full 3D environment simulating, atmosphere, the real world, thousands of independent, artificially controlled agents in the game. And so on. So you can see this various progression in Mortal Kombat, one of my other favorite game series, Quake, which is another first-person shooting game, and then, of course, the Doom series, which I think has had a lot of influence on computer graphics itself, even to this day, from early 1993 to 2025. I wonder if anybody's played any of these games. You can maybe show me in the chat or if you've heard of these games. I know they were quite popular in the US when they came out, but I think Doom is probably the most famous that has made it much around the world. And famously, almost every device has a compute unit can run the game Doom. from toasters to microwaves. Yeah, some folks have played Tomb Raider years ago, so so I'm a big game player. So if that's something you're interested in, yeah, some folks have played most of them. Great, great, glad to see that. So again, maybe you don't care about video games, though. I know it's something I care about, but if you look at other domains, things like finance, and it's hard to find exact figures on this because they're sort of protected data in many ways. But if you just look at the amount of transactions that are made, whether for banking or high frequency trading per nanosecond at this point, it's just really incredible the type of software engineering that goes into these systems. And throughout this slide set, if any of these domains are interesting, I've tried to include a lot of talks, many of them from CppCon, some of them also from CppCast, which I know some of your members have been speakers at, just to take a look at. So feel free to explore those. Then, of course, if you look at supercomputers, it's kind of mind-boggling to, again, understand what these numbers mean. I wonder, having 1 million CPU cores, I can sort of understand my machine's got about 16 cores on it right now, but when you get to 1 million, that's really amazing. So what kind of things can we compute? And famously, there's a movie, Hitchhiker's Guide from the Galaxy, which is based on the book, The Hitchhiker Guides of the Galaxy, and its series, in which they build a supercomputer to compute the meaning of life. So anyways, you can read a little bit about that for fun. But more seriously, I think we can compute lots of things in health sciences, energy, environment, and so on and so forth, that are going to make the world better for us, right? And we need that performance to compute these complex simulations and so on. So let's revisit back video games, since that's again my domain, and try to understand what these gentlemen were thinking about. So this is John Carmack and John Romero, the Johns, who were the original, two of the original programmers, the early days of id Software, way back in 1993. And what's interesting about this game is the type of machine. Again, it was running on 30 years ago at this point. They were, machines running at 100 or 200 megahertz, which was, again, perceived as fast at the time. But for the amount of work they were doing, they really had to know their stuff. They really had to know their computer science. They had to know what exactly their hardware was doing to get every instruction or every cycle, so to speak, out of the hardware that they had. So I like even studying this game today, it's still relevant to understand some of the tricks and optimizations that they were using, because our software that we write today still needs those same tricks and optimizations. And still, as programmers, we need to understand our hardware. So they did a lot with a little, which is something we could maybe even draw inspiration from on our machines that we have today. Still trying to, again, be good programmers, even though we have more resources. And it was through these programmers that were really pushing their hardware that it ended up changing the industry, or at least I'm going to make the argument that it changed the computer industry, because the people that wanted to play these games wanted the best graphics, and then there was this demand for graphics cards. And now today we have discrete graphics cards in many of our machines, or again, even in my cell phone, regardless of what phone you have, it probably has a separate or at least a shared piece of hardware for just doing dedicated graphics work, which is really incredible. And again, I credit games for really pushing the need, at least to the broad consumer. So that's the idea here. So anyways, you can follow the history of gaming as we did early on and see the improvement in graphics as our hardware gets better and our graphics capabilities improve. So again, these are just, again, some screenshots of the improvements of the games. And again, more on my argument that, gaming and just doing cool and interesting stuff pushes us forward. There's this interesting cycle of better software demands better hardware. We get better hardware, and then we can do more with our software and so on. Or at least that's what I would like to think, or for us as programmers to be sort of inspired by, so that we really do get as much as we can out of these machines that we pay good money for. Okay, so anyways, you can see this sort of exponential growth again in graphics. We've already gone through that with several different games, but I think it's just interesting to see along with this graphic how even methodologies of how we program these things changes to match the hardware, right? We have on graphics cards now programmable shaders that have become more and more generally programmable, so they can do things that are not graphics tasks if we understand how our hardware works. So again, this is just kind of a nice illustration of that. And of course, this diagram only goes to 2012, but you can go to a website and just see how much the graphics have improved. Sometimes it's hard from a distance to tell if things are real or a video game. So anyways, as I mentioned, both the Johns and in particular, Michael Abrash was an interesting programmer at the time who, again, they brought onto the team, I think when they were working on Quake 1, might have even been earlier on with some of the Doom 2 or other games, but I believe for Quake 1, to really squeeze out every cycle. And Michael Abrash wrote an interesting book called I believe it's called The Black Art of 3D Graphics Programming, that again is still an interesting read today. You can find freely online. Yeah, and a question coming in, is it safe to say game requirements at the foundation of AI training possibilities? I absolutely think so. So I think, making the case, at least up to this point in history in 2026, that games have been a massive driver in the innovation of GPUs. But we are sort of seeing this shift now this year, 2 years ago, with large language learning models and the AI workloads. That's probably maybe more driving what's going into our graphics cards now. And they're even in some cases being marketed as, neural compute units and AI compute. So maybe we'll see a discrete AI processors coming up soon. That's, again, GPUs sort of doing the same thing, and how we train, or the algorithms we write, and we write in a way that they execute on GPUs in parallel. But it's very interesting you bring up that point, because probably the next decade will argue AI is actually the main driver. All right, great. So when it comes to understanding performance, or rather unlocking performance, we have to understand our hardware. I've got this quote here, and then we'll get into some of the more technical stuff, but it's performance is the currency of computing. If you've seen some of my talks, I've used this quote a few times. I like using it because it's just resonates with me very much here. And it was said by this professor, Professor Charles Leiserson. And the point of it was to say, if you get performance, then you can often buy properties of software with that performance. So for instance, if you're writing an algorithm that can compute something very quickly when you're drawing on the screen, you can show the user more pretty graphics. When you write software that runs faster, or under the sort of budget of how fast something needs to write, then you can add safety checks, more properties there. So it really benefits us to think about how can we get to get every ounce of performance out of our machines. So this, again, is where our data structures, algorithms, and so on knowledge matters. So anyways, let's get into our goal here of learning a little bit about hardware. And again, if we understand the hardware that we're writing code that executes on that hardware for, we can buy performance and build cool applications, improve applications that exist, and so on. Okay, and we're going to focus mostly on the CPU today. Again, I know I talked about graphics a little bit with GPU. That could be a separate semester of talks, or even tensor processing units for doing AI workloads. But we can start with the CPU and understand how these work. And in fact, a lot of the principles, including the principle that I'm showing on the screen now, apply equally to GPUs and TPUs as well. So graphics programming units and tensor processing units. But if I had to pick the most important rule just to ground us, it's this rule or principle of locality that states that programs tend to use data and instructions with addresses near or equal to those that they have used recently. Okay, so what's this mean? If I kind of lay out a data structure like in this image on the right here, let's say it's an array, I tend to access maybe a particular value in that array, or maybe a variable, over and over and over again, right? Because the programs that we write are loops, simple as that. And then again, with that idea, spatial locality means, again, data that's close. So again, could be values stored in an array are right next to each other, so spatially very close. We tend to iterate through things linearly versus jumping around in our algorithms. So based off of this assumption, or at least rather, this is the assumption that we can build into the hardware to make things fast, okay? If we know where something is. And sometimes I use the analogy of when you're shopping or at a grocery store, right? When you're shopping, you tend to pick up items that are next to each other. This is why, at least in US stores, they'll put something like chips and then they'll put salsa or a dip right next to it, right? Because you're probably going to buy one if you buy the other, versus having to do the effort of running to the other side of the store to pick up some different item. So you can think about grocery shopping later when you're buying food at a store, market, or wherever. Right? We put things next to each other that are likely to be used together. Now, again, some of you might know this concept. I know you've got some great systems programmers in the audience here. But you can also maybe think about this in terms of other things. Again, if this is review for you in terms of maybe compiler optimizations, when you use keywords in C++ like inlining or forcing inlining to put data next to each other, how that can help you, or help the hardware rather, predict what's going to happen. There's other sorts of optimizations like loop unrolling, whether you're doing it yourself or letting the compiler do it. So that can be other ways to think about the optimizations that you're writing in your code or when you're trying to carefully craft code together. So since I've been talking for a little bit, let's give you a chance to think here about this piece of code. So I've got a piece of code here. It's an okay piece of code here. We probably shouldn't pass in a pointer, right? We should use like a span or something, or use std array. But that's besides the point here for what I want to talk about. So I've got my footnotes there. And the question I want to ask is, if we're iterating through this data here, and we're doing this in what's known as a row major order. So looking at the loops, we're going to go across the rows here, where my cursor is, then back across the next row, and back across the next row. Does this generally have good locality? What would folks in the audience think about this? Get a chance to think about it. You can either unmute or just type out in the chat, and I'll repeat what's being said there. Yeah, so there's a question, what if we swap these? So I think that's implying, this is potentially, maybe this is a good order, maybe not, but there is something to this swap here, right? This order that we're iterating through the loops. So we swap I and j. That is the question here. Whenever I pose questions, I like to make sure that you can be right no matter how you answer. But as long as we understand the foundations of the why here. So let me give folks a few moments. I see there's some folks in the chat right now thinking about this. Does this have good locality? Yeah, okay, maybe there's a lot of things we can think of, but let me give you I think row major has locality. Yeah, okay, great. There's somebody else thinking. I'll let them think here. I'll advance the slide one, right? So if we're reading our data in this order, one after the other, that's kind of what we define good locality, right? And specifically good spatial locality. Things are next to each other in memory. And then we'll read the next row and the next row and so on and so forth. Okay. And now what if I do the switch? I'll give folks time to think about this, because this was exactly the question that came up in the chat here. Yeah, we get bad locality because we're jumping each time. All right, yeah. But, so that's one comment. That's sort of leaning towards folks, but there's another comment in the chat that said, but column major doesn't. I also think it depends on how much memory the CPU can fetch. Ah, okay. So maybe, yeah, now we gotta start thinking about how much memory we have here. So let's illustrate the point here that if we're reading memory from here, and basically the hardware is expecting, again, because of this principal locality, that we're gonna fetch the next data. And maybe even most of our machines these days are trying to prefetch data as well. There's different ways of doing this, predictive ways, and there are, of course, speculative ways to pull out data and execute. But what ends up happening is we end up needing this next row here as our data is organized, okay? So, of course, that's going to be a problem because, well, we've done all this work potentially prefetching the next thing, and then our prediction was wrong, and we're going somewhere else. So, we can't sort of optimize that code here. So bad locality there. I think it's important too, if I sort of just illustrate, I've drawn this in 2D, but again, remember our memory is actually laid out just, one address after the other, whether you want to label it top to down, top to bottom, or left to right. This is what's going on here. We read here, we attempt to prefetch. The next read is actually here. So this is the same illustration, but just in the linear way that our memory is actually organized. Now, the comment was also in the chat that says, what if we could actually fit, or maybe our prefetch is, this entire length, in which case we would have all that data anyways. And to that point, yeah, you're exactly correct. It's not going to matter on a small problem, or small enough, as long as we know how much data can fit there based off of how it's organized. So great. And we're going to learn about the hardware component that stores this data, the cache, and maybe our cache can, at various levels, store all of this data. In fact, it's very likely that for this size problem, it can. Okay, great. So, I ran some benchmarks of this, and this is what you'll find in the source code, a few snippets, just to see how costly is it. So if I have 40 megabytes of data, and I'm just doing this simple task of maybe summing if I do the good locality version, about 3.8 seconds versus basically 2 lines of code, just flipping them. So that's really incredible. In my mind, that's very incredible, the implications of that. Okay, so now we want to measure the performance. So, I have a little tool here, time. I'll just highlight it in this slide that you could use here, and that'll give you like an approximation. But again, we want to understand a little bit why, and maybe get a little bit insight to software engineers about what our hardware is doing. And again, anytime somebody gives a talk on performance, right, they need to justify why and actually measure, because there is a lot of hardware out there. Again, the computer that I'm presenting on is going to have different performance than maybe this phone because it's different hardware. You have to know our hardware. Okay, so a great tool that you could use is called perf. I'm just curious, how many folks in the chat have used perf by chance here? Has anybody used or seen this tool? It's a profiler on Linux. There are similar tools on Windows through Visual Studio, or on Mac has instruments built in. But I suspect, yeah. Great. Yeah, so anyways, here's, yeah, great, a lot of thumbs up. Here's, again, the a performance, another performance, a smaller size here, so about, what was this? This was actually supposed to be about 12 or 13 megabytes, so two and a half times worse. If we, again, try to understand this benchmark with perf, it gives us a lot more output. And what perf does is it has these performance monitoring units, PMUs, that basically monitor how long something's taking in the actual hardware. So that's what makes it really useful. It has these hardware counters to tell us some statistics. So we can get these sort of statistics or these stats here, and you can see the columns version, which is slower, and compare it to the rows version. And we can try to see, why something is slower here. And we can see maybe of course, we can see the time. So in this particular run here, this was like 6.5 seconds versus 2.7 seconds. We can see some other things like how many instructions there were. And we can see other things that should be kind of similar because they're similar pieces of code. But again, what's the actual thing that's slowing down the performance? Because, I've just got these large numbers here. And the actual, thing that I actually want to pay attention to is probably more towards the bottom right here of how many instructions are being retired. And what this means when an instruction is retired, that means it's been complete. We've completed useful work. So I can see here a little bit more green around, instructions that are retired, meaning we're not repeating work. We're not speculating as much. We're doing the thing that we told our machine to do, to take some task, complete it, and finish that task or retire that task. Okay, so let's understand a little bit about our hardware now that we have a way to look inside of it with a tool like Perf. And what we really want to understand is this thing called the cache here, which is really, really important for understanding spatial locality. So from a programmer perspective, I typically think of things in this view, which is great. The operating system takes care of giving us this view where I basically just have a computer and then I can put stuff into memory like integers. Okay, so in this picture. But what really happens is there's multiple layers of memory here, right? We might have this memory that I'm highlighting is our dynamic RAM or DRAM, the main memory. Of course, have a hard disk, but closer to the CPU, we have something called a cache that's a smaller, faster memory. It's got a little bit of a different job where it makes it smaller and faster. It doesn't have to retain the information, but it sits much closer to the CPU. So the distance to take that data and put it onto the CPU is much shorter. And again, this can be a faster piece of hardware. So that integer actually is copied here into our cache, and that's what we want to read and execute from our CPU, and then ultimately put that into a register. And again, as mentioned, there might be multiple levels of these caches. Some of them are shared across CPUs as well. But we want to sort of be working with our data in this layer here, this level 1 cache here, because that's the shortest distance we can think about it, just in terms of how close it is to the CPU. And that, by orders of magnitude, makes it much, much faster for us to access and do computation. Okay, now again, because we learned about spatial locality, and this is where the concept kind of comes together, is when we have one integer, we're not just bringing in at one integer across every cache. We're bringing in what's called a cache line or a cache block, multiple of those integers. Okay, so we got to copy all of them across to each of the different cache lines. And that's, again, where we get our performance, because I don't have to look up one thing at a time. I've got my however many integers here in or near my CPU in the level 1 cache. Okay, so typically, this level 1 and these cache line sizes are around 64 bytes, and that's a common number on hardware, but you have to check so you know. You can have multiple of those cache lines, 64 bits in this, 64 bytes, excuse me, in this L1 cache. All right, and then somewhere down here is where the what's known as a prefetcher is, that's going to try to predict what data am I going to need, so that it can, again, if it needs something else, go and check in the next level, and the next level, and the next level, and so on, and eventually bring that into the L1 data cache or instruction cache here to do some computation. And again, this is why the access patterns matter, because we want that spatial locality. So again, we can have this really nice sort of pattern of accessing our data versus again, where we're jumping all over the place here. Now again, there's always an asterisk next to these things. If your hardware, for whatever reason, is column ordered, maybe this is the better access pattern for your hardware. So you just have to know. You just have to know or be able to read. And how you know is you take the actual Intel or AMD or Qualcomm, whatever processor that you're running on, Apple Silicon, and you look at, or the actual hardware. Somebody would have documented that either in a talk or in the hardware manuals to understand if it's a row major or column major architecture. And there can be other interesting patterns here. Again, for those of you who've done some GPU programming, or maybe you're looking at these, breaking up these tasks into tiles and accessing data in different way. Again, just different access patterns. So anyways, now that we know about this idea of what a cache is, and something that's actually on our hardware that I'm claiming is going to give us performance because it's the physical design of the cache is designed to do this task of looking up and fetching data very quickly. We should actually, in our perf tool, we can look up, and I'll just highlight it with my laser pointer here, the cache misses. So we can try to find out when we're sort of speculating or doing this predictive prefetch of what's going to come in, how many times do we hit that data and how many times do we miss that data? And cache misses are going to be bad for our performance. And if I look at our columns version where I have a bad data access pattern, I can very clearly see here I'm missing 183 million times versus 700,000 times in the rows version, right? So we can see where there's like 3 orders of magnitude there. That's that to answer why our performance is bad. And then the branch misses are, again, something to do with the predictive, what instruction am I going to sort of execute next? Since a lot of this work's done in a loop, that's not as bad of a problem, but it truly is the memory lookup stuff in our cache that's causing us problems. So anyways, I have a little illustration of this, again, just to, again, make the point of the L1 cache, L2, and then maybe our main memory or L3 level caches, right, would fall later here. And let's say, again, our CPU processor's right here, and I want some data to travel to the processor. We can kind of simulate this like a race here. An AI in this case will just be, I don't know, some artificial intelligence algorithm here. If you've been at a, I don't know if they have these at the World Cup matches that are going on, but certainly a lot of events here in the US, they have like these races here. So anyways, you can think about this as a race here of how fast can our data get into the processor, right? And clearly, right, the data that started in the L1 and L2 cache was much faster. And if we've got to go from main memory, it just takes a lot longer. So hopefully, that's pretty obvious. And again, memory often is the bottleneck here because, well, while our processors have gotten faster over time and continue to get faster, we can actually scale up how many cores we have on our machine, and that can be a really cheap way to say, oh yeah, we've doubled the number of transistors and thus processing power we have on our machines. The memory speeds, on the other hand, haven't gotten faster at the exact same rate. So oftentimes if we're waiting or mispredicting where we're going to put memory into our CPU, which actually does the work of processing the data, that means, if we're waiting for our work, our programs aren't going to get much faster. So we say we're often memory bound or IO bound when we're waiting on getting the right data into the CPU. And that's why it's so important to get into these caches, which are our fastest pieces of memory outside of the actual CPU registers. Okay. Now, again, you can look up on your operating system the cache sizes. Here's a few just in the Unix header if you want to do this in a C style. Does anybody know the C++ functions or have looked at them on CppReference for that'll give you your cache line sizes? It's kind of an obscure name. Yeah. Okay, yeah, a few folks are saying yes, some no, but it's like, I don't know the full thing, but it's like std, : hardware destructive interference or something like that. It's kind of a fun name you can look up on CppReference. But that would be the sort of portable way to do it, just using the C++ standard template library. Right, so C++ has some ways to look this, some of this information up. All right, so let me pause there for a moment. Any questions about the cache or sort of understanding the importance of this and getting our data in the right place? So here are a few of our slides here. Here's our cache. We talked about data access patterns, measuring and finding cache misses, and so on. All right, I'll continue on here. So now that, again, we know about how important memory is and some of the implications of just how we structure our code, let's again try to understand a little bit more about our CPU chips here. So typically, again, if I'm teaching this for the first time, or if you're looking at this for the first time, here's kind of a layout of a CPU, a computer chip. Basically, again, we have what's known as the ALU, arithmetic logic units. Those are the things that do the actual computation when we're adding numbers and so on in our machines, right? Our computers are basically really good adding machines. They fetch data from registers, and typically you've got maybe 16 general purpose registers, and then some other registers for doing floating point computation and so on, but just a really small amount there. And those registers are often populated from data on the cache. Again, why is the cache fast? Well, the L1 cache, again, is on the CPU chip. And then if that data that we're requesting isn't there, then we need to basically travel across I/O and go into the next level of cache, and then ultimately main memory or the hard disk to look for data. Okay, so that's sort of a view of a CPU chip. And I think having just this model is a very good way to be thinking as a programmer. But of course, we can push things a little bit further here. And of course, this is why folks tell you, if you have more RAM, this is a way to speed up your machine, right? Because RAM's pretty fast. You definitely don't want to go into your hard disk. Now, unfortunately, RAM prices are very expensive as of this recording in 2026. So, do what you can with what little you have, right? Just like the original Johns in their Doom programming days. All right, but I thought it would be interesting to actually look at an actual CPU. Get a little bit more of a deep dive here, just so we can understand what's the next level beyond that sort of simple mental model to have of our machines executing. So I want to just give this as a little bit of a preview. And you can find some of these chips. I think the website's no longer available, but it was called WikiChip. But I've got a link here to the web archive that has these very beautiful diagrams. So you can try to figure out what CPU you have. And what you'll basically find out is that your computer's divided up into like a front end, there's a execution engine, and then there's the memory subsystem here. So we can kind of look at some of these individual components here and see, again, just all the work that goes into our CPU. If you kind of stare at this long enough, any one of you could understand, a lot of these parts here, right? So, let's try to break it down just a little bit. We don't have to do a super deep dive here, but I think it'll be helpful for understanding things of performance. I'm going to think of this sort of as a starting point, meaning when we load and start executing a program from the operating system, that might come from main memory or the hard disk, but eventually it's going to propagate its way up into the level 2 cache, which is usually the last level of cache on a CPU. So we want to be able to load in that data. And then basically what we're doing then is then we go into our front end here, and this is where we're going to start fetching, coding, our instructions, right? So actually looking at the memory and saying, okay, I've got these pieces of memory. This correlates to this add or copy or divide instruction or whatever it might be. It's going to also cache some of those instructions and start fetching, decoding those instructions. And it could do this in parallel, maybe multiple instructions. And then it's going to start queuing them up here. Or the execution, which is our next part that I don't have highlighted. Now you'll also notice here, though, as we're executing these instructions, right, doing the fetch, decode, execute, there's this other side here where you can find the branch predictor. And that was one of the parts or one of the pieces that was saying, well, you want to speculatively predict what's going to happen next, right, based off of maybe the instructions we're loading, okay? So you can see these pieces and how they sort of come together. And then, of course, we get into the execution engine, and this is where the actual work is done. So I know what instruction I'm going to do. I'm going to do an add, subtract, multiply of numbers, whatever the reason might be. And then basically I want to execute there. And I have these specific execution units that can do work, adding, multiplying, etc. on integer data or floating point data, as you'll see in this diagram. Okay, so again, this is the rough sort of flow here that things actually work on. And if we're trying to understand then our data access patterns and where we're being slow, so in our previous example, we were slow because we couldn't populate the correct memory, right? That tells us that maybe in our front end, that's where our actual performance is. So we can kind of use these profiling tools to understand, are we slow on the front end, the execution engine, or the memory subsystem where we're again looking for data. So hopefully that makes sense. And again, it all connects here because once we execute something, you then have to store the result in memory, and then the cycle repeats. Okay. And again, today we've sort of seen that we've stalled, or one way to think about this is we've slowed down our execution unit because our CPUs are very fast. Remember that memory and processor gap. We just weren't able to populate enough data quickly enough because we were predicting the wrong data. And our slow part is this memory subsystem here, right? Fetching the right instructions. Okay, let me pause there for a moment if there's any comments. Exactly where on the front end that is slowing things down. Yep. Yeah, so perf has event counters for basically most of these individual components. You can do this sort of analysis to figure out, yeah, exactly where you're going wrong. So we looked at one, for instance, like the branch prediction as a particular event. In fact, if I go back, let me go back just to where I showed those flags, because I think it's relatively close here. Let's see here. Wherever I added in our cache. Yes, over here. So these are so when I do sudo perf stat, so get the stats here, -e will monitor for specific events, and these could be things like the cache misses, branch misses, and there's actually the amount of things that you can look at in perf. There's like hundreds of these performance counters, so you can pretty closely monitor for your hardware where it's actually running slowly. Great question. Yeah, and then oftentimes what you'll find if you look at I think it's the perf site, or maybe Intel's got some tutorials, they'll do this sort of profiling based off of MI slow in the front end, back end, and these types of things here, which I think is really, really neat. I think it's a nice way to think about profiling beyond just looking at time or instruction counts. All right, I'll just pause for other questions. All right, great. You are here. And feel free to keep asking questions, but I'll just put this aside here. The story gets a little bit more interesting when we have multiple cores as well. Again, since this is sort of a back to basics talk, so I'm not going to dive too much into it. But the one thing that I want you to know is that when I have multiple cores, we do have to think a little bit about the synchronization of our data. And in some cases, the spatial locality can actually hurt us, again, if we don't synchronize properly, meaning if different cores are accessing neighboring data, we can run into something that's known as false sharing, where we write to pieces of memory that are in different cores, different CPU cores, cache lines, and that can cause a little bit of a problem because we've got to sort of ping pong and relay the data back and forth, and that can really slow down our hardware as well. So in multi-core CPU programming, there's still yet some more things to think about on our data. Now there's a question about for branch misprediction, how can we mitigate that? Can we help the CPU be better at predictions, maybe by optimizing the code? Yeah, that's a great question. Second bit of this talk here, I'm just going to briefly show some slides on various compiler optimizations. But you can basically help your program not have to guess by not having to jump. So anywhere where you have a branch, so an if statement, a for statement, right? Somewhere where you're jumping code, how can we get rid of those? Well, we can do things like unroll our loops, we can inline code, And then the CPU doesn't have to guess, right? Because it's literally just executing the next instruction on the performance counter. Now, there's other things you can do, because maybe you say, well, I do need an if condition somewhere in my code. But there's this field of programming or these techniques known as branchless execution, where you can basically put into memory based off a branch, and then sometimes that can remove branch prediction. You still have to measure. But again, yeah, those are great insights to have. How do I help my hardware, right? If I see, for instance, that we were mispredicting a lot, in a way you can try to do this as a micro benchmark, right? Write a piece of code that has a giant switch table, lots of if else statements, and it's just generating random numbers for which branch to take, and see if you can get your CPU to perform badly at a particular spot. That's another way to sort of understand things. So if you're not sure how to like write the optimal code, say, well, what's the worst code that I could write? That can also be fun. So yeah, thank you for the question. All right, so yeah, just to illustrate on this multiple cores here, on many of our desktop or laptop machines, the level 3 cache is often the cache that's shared. There could be a fourth level, it depends on the hardware, but usually the third level of the cache is shared among CPUs. So that means you do have to be careful if data sits on the same cache line. So again, just going back to that point. And again, this is this idea of cache coherence. So speaking to my last point, this can be a fun example of trying to write bad code if you're interested in threads to try to see how bad you can make the performance by accessing data in different threads that isn't or that is on the same cache line. And how to prevent that? Well, basically spread out your data and whatever your L1 cache line size or L2 cache line size is enough so that the threads aren't accessing the same data. All right, great. So yeah, so this gets us into this idea of, okay, we know about the hardware, we have some ideas about the cache being important, we can monitor it. What are some trade-offs? In this part, again, I'm going to go through relatively quickly because I've given a few talks on it, but I did want to put all the slides in one place because I think folks are curious in compiler optimization and so on. But there's this really nice book. It's an older book. It's still relevant today, called Writing Efficient Programs by John Bentley. And basically, he gives us some of the different trade-offs of how do we get performance, right? And if I want performance, well, there's different, trade-offs basically we make in computer science. Space for time, so I can pre-allocate some memory or pre-allocate some results. Things like const expr, const init, const eval in C++ are very useful for this, where I can kind of pre-allocate data and compute things during compile time, as an example. We sometimes trade time for space. So for instance, if you have a zip file or you're watching a video like this one on YouTube later on, right, we can say, well, I'm going to spend some time to sort of decode the data, whether that's the video data or unzip the file, because it's worth it to have more compressed data, right? It's less packets of information to send over the internet, and then I can do it more quickly on my machine. And then, of course, sometimes you can get space and time. You can get both of these, or lose both of these. But anyways, those are the classic sort of trade-offs here. So I'm just going to go through a few, just so they're sort of on our radar here. Things that you can think about in regard to performance, but we can do things like modifying the algorithm, choosing a better sorting algorithm, choosing insertion sort when you have a small amount of data versus merge sort when you have also a small amount of data. But typically, you'd maybe choose merge sort or quick sort when you have more data than say like what would fit in a cache line. Okay, so anyways, you can choose the different algorithm. I'll focus again on data and data access patterns here because that's what we've been talking about, or optimizations that enable those. So again, some examples of just paying space for more time. So if we have some data structure like a linked list, for instance, and maybe we need to traverse to the head of the linked list a lot or traverse directly to the tail, right? We could just pay a little bit of extra space to store pointers to the head and the tail as needed here. Another kind of classic example of paying space for time, and this is where C++ can be really useful with constexpr, is if we're computing like the Fibonacci numbers. This is the recursive solution that folks might learn when they're first starting to learn how to program to compute the next Fibonacci number. And you can see sort of the visual representation of how this works here by recursively calling the same function, recomputing the same result, and then recursing on all the previous results to build a sum. That's very expensive. In fact, for this example, I think I'm computing the let's see here, the 45th Fibonacci number. That takes about 10 seconds. If you use a little bit of space to pre-compute or store the values that have been pre-computed here, the sort of caching those values in sort of like a software cache, right? Keeping track of these values. The result, or the time it takes to compute the 45th Fibonacci number is, does anyone want to guess or has done this experiment here? I'd be kind of curious. I wrote it in C. You could write it in C++ and probably make it constexpr and do some more interesting things. But we're at 10 seconds before, which is kind of crazy. For this one, it's 0.002 seconds. So what is that? Like several thousand times faster, right? Just by paying a little bit of memory, right? So we'd like to make that trade-off, right? As an example. Okay. And then this also goes back to, if we were to measure this and see where we spending a lot of space, we would see more cycles. This is a recursive function, so we're jumping a lot. Maybe we would get more mispredictions, for instance, of where we're going, because again, anyway, so this is a really nice example here. Okay, so anyways, these are just some notes on this here. In games, we do this all the time. So here's a few visual examples, like computing lighting. That would be really expensive to simulate the universe in a room, meaning every particle, every ray of light that I'd have to simulate. That would be very expensive. So typically in a game, we fake the lighting by just drawing where the shadows would be. This is still true in whatever fancy games that you see coming out today. They'll maybe pre-compute some of the lighting, or only have dynamic lighting for a small section of the game here. So anyways, this is a nice example here. And you can see it in a few different areas in this screenshot. Okay, some other tricks for performance, paying space for time. Again, is if you are going to allocate things, you allocate them up front, any of the memory. We're going to be storing things like Fibonacci numbers, whether that's static data in the executable, or if you're going to do any heap allocations, you heap allocate as much as you think you'll need, and hopefully no more right away. Right, there's sort of a classic trick, if folks don't know, in C++, where you can, if you're working with a vector, for instance, you could create the vector and you could do, vector dot reserve to basically reserve your memory up front, right, and have that capacity. That can speed up your memory allocations or how you use that data structure quite a bit. Okay, so just on the other categories to show a few things, paying time for space. If you get a chance, this is a really cool video about how they made this video game here. I know I'm highlighting a lot of first-person shooter games, which you might or might not care about, but you can look at it, and if I told you that the actual game here that you're seeing takes up less memory than the actual image that I pasted in, you'd say that's pretty incredible, or at least I would hope you'd say that's incredible. So this idea of packing and compressing data is really powerful, and this is an example of paying time for space. So how the game works, right? It's 96 kilobytes roughly of source code, but it unravels and generates data as you go, as you need it. So this is just kind of neat, and there's a lot of awesome optimization techniques. If you have during your dinner or breakfast, watch this video. If you can convince your family members to also watch. But anyways, so along these lines of packing and compressing data, there's a few other interesting trade-offs still to think about here. I mean, of course, we've learned this magic size of about 64 bytes about fitting data into a cache line for most architectures. That's one, right? So again, if your range of data is only, integers, integer values from 0 to 255, right? Use unsigned char types, for instance, because you can pack more and get more data into that cache. So anyways, keep that in mind here. There's a few other interesting optimizations. Again, looking at older video games and how they stored animation. They pre-computed a lot of the mathematical values that you would need. And this is a trick, for instance, there's no point to recompute the value sine of 0 or cosine of 0, right? Your trigonomic functions. These ones tend to show up a lot, like cosine of 45, cosine of 90 degrees, etc., right? So don't compute those, right? Just look them up in a table, or have them as consonant values or something. Okay, so I'm going to skip this part because it's getting into some of the 3D stuff, but feel free to check out the slides if you want to see how compressed they are. The one thing I'll just note is that they're using unsigned short values. Again, knowing what your data type is, and they've got a lot of tables to just look up indexes of data here. And conveniently, in some cases, that makes this particular vertex a 4-byte value instead of being 5 bytes, which would be padded out to an 8-byte structure anyway. So anyways, you can get a lot of extra data there. And there's lots of other interesting ways, but this will have to be a graphics talk later to talk about how to optimize meshes. But for those interested in graphics and gaming, feel free to take a look there. Now let me get to a few other optimizations here regarding spatial locality. Again, packing all of your data in a single file can be another way to get more spatial locality. So this, again, is one of the tricks that the Doom games used. That way you don't have a file system to go through. You just have your one chunk of data that's loaded. You don't have any extra bits for like the file names and stuff. So anyways, this was another trick where we were paying time for space. Kind of that same example of basically what a zip file is. Or when you download or watch the streaming a video on YouTube, right? Your computer's the one doing the computation as it decodes the data that's sent. Okay, a few more categories here. Space and time, this is the one I wanted to get to. Then I'll do just a few more, and then we can break for questions. But this is kind of an interesting one here where, we've talked about how much data we can fit into the cache. And so we'd say, yeah, let's save every single bit that we can. So let's say we want to represent time with a year, a month, and a day. One thing we could do is we could figure out how many years, we have been through. So if I have 13 bits, that gets us to about the year 8,192. So, on the calendar that I'm following, right, we're at year 2026. So, we have plenty of time here or before we'll need to upgrade that bit. But we can save, right, versus using all 32 bits for the year, for example. Or if we had a short there, right, with 16 bits, we're still saving, 3 bits there. So, and then we can do this accordingly for month and day here and so on. Now, one pragmatic thing is most of our compilers, C++ compilers, will probably pad this struct out to default unless you say otherwise by setting the align as or I think pack is the pragma. You do like pragma pack with 1 bit or something. But this will still pad it out to 32 bits, but that's still much smaller than if I had these 4 integers there with 96 bits. So anyways, about a third of the savings there. Now, the other caveat too is our computers, our chips do like, usually 4-byte aligned values. So again, there might be a little bit of decoding here, but again, it might be worth it. Okay, SIMD is a trade-off where you can get time and space by doing things in parallel. Again, I don't really want to talk about parallelism here, but there is a new std SIMD library coming in C++26 that I haven't seen many performance numbers that still beat writing your own SIMD code in C with the new C++ stuff, but over time I think it will get better. And it's at least nice it's there so people know SIMD exists. So. All right, let's talk a little bit more, getting into sort of a last category of things, the structure of our code, so we can think about the data access patterns here. And again, when I think about structure of code, I'm thinking about things like loops, functions, and so on. So a few optimizations for folks to know about and to take as trade-offs here. This is kind of a fun one that your compiler might perform. It's called code motion. And what I'm looking at on the left here is, I've written some function here to approximate pi. 22 divided by 7 gives me 3.14 or something. Anyways, I just needed an example. And let's say then that I want to compute the circumference of some different values, right? The area around the circle. And so I need to do this 2 times approximation of pi, right? And well, I notice that basically 2 times this function call here, I'm repeating that work basically every iteration of this loop here. So the idea of code motion is to say, hey, let's just compute this 1 time, actively caching or storing that value in memory, and just put it above the loop here, right? That's the idea of code motion, and your compiler might do this for you. But knowing what we know about hardware, this is kind of an interesting trade-off because, well, what's going to happen here is if I actually run this code, what intuitively seems like the smart thing as a programmer to say, hey, I'm going to do less work in that loop. The example on the right actually came back slower. And it came back consistently slower as well. So this wasn't just a error here. But why could this be? Well, knowing what we know about memory, what do folks think made this code slower here? I'll give you a chance to think about and answer this. I've got the computation here. And remember, what are our computers really good at doing? Or I should say, when I think about the evolution of hardware, what's gotten faster over time? Our CPUs that do the work, or our memory systems? That's a little bit of a hint here, even though we were introducing that topic nearly 40 minutes ago. I see some folks thinking about it in the chat. Yeah, memory is much slower and hasn't caught up with the CPU speeds. Perfect, right? And exactly what we're doing here, right? When I'm doing this pi times 2, this value here that I'm actually looking up in memory here, potentially, right? Maybe I've gotten worse temporal locality for whatever reason, and this value is not staying in the cache, so I've got to do a memory lookup every time here. And if that memory lookup is slower than the actual computation, which this is a pretty trivial computation, right? 2 times whatever this function is, it's better to just repeat the work and do the computation, right, from a performance standpoint. So we should keep our CPUs busy and just keep the code on the left here, right? So this is a tiny example, but it's, again, kind of illustrating the trade-offs and again, the importance of understanding what our hardware is doing. And when we're writing code, are we looking up things from memory? How much did that computation cost, or should we just repeat the work? And in many cases, if we go, or so about graphics cards and graphics programming, what I'm trying to say is, we often do not store stuff on our graphics card in memory because it's fast to compute. That's what those machines are built for, right? Just crunching numbers as fast as possible. All right, so anyways, yeah, memory fetches here is the issue most likely. So we want to be careful if our compiler did this for us. But anyways, I don't want to walk through all the samples here. You can kind of look through them, and they're also kind of fun exercises after this talk to sort of check your understanding of what we learned about. But things like early return, for instance, can be useful from functions. The other big one is loop unrolling. So, doing like a static for each loop and kind of unrolling it at compile time, or that's kind of what you'd want to do. Or you can again let the compiler do it. Where somebody was asking earlier about branch predictions. Your compiler is probably smart enough to figure out that we're going to jump back to this loop. In fact, that's probably what it's going to predict we're doing every time, right? It's going to maybe have a label for this loop that it knows to jump back to and keep track of that. But really what we could do here is we could take these lines 9 through 11 and just simply make it this line here. And just say, hey, let's just sum up everything instead of having to jump back to the loop and make sure that we've done the jump correctly. We don't have to test the condition. We don't have to increment whatever. We've just got the values here. So that case, we're probably paying maybe space to unroll this loop depending on how big it is. In this case, it's not much bigger. But again, we should be able to get more performance there. All right, and we can do this partially as well, depending on the type of problem that you're trying to solve. Now, again, there's different variants of this. Okay, and then there's other fun things like loop fusion. If you're working on different parts of data, just putting them in the same loop, so you don't have to, worry about mispredictions or anything, or maybe you can use the same value I here, which is already stored, potentially in a register or something. So anyways, that's the idea here. Okay, and then there's a whole other thing that, and this is the part that your compiler is pretty good at, but generally what I'd say is if I know I want to do something efficiently, I'll just do it. But for instance, let's look at an example of like the natural logs here or something. Right, this property of adding them together is the same as just doing the multiplication here. Right, that's something that I could probably just do, or I know, or maybe these trigonomic functions. These are some ideas. Or there's the common like plus plus I versus I plus plus. Compiler is probably going to replace those, but why leave it to the compiler to do any extra work, right? Just do the substitution yourself. Okay, so I got a bunch more graphics examples here. Early exit on like distance checks if you're trying to detect if two circles overlap and so on. There's different ways to structure that. The other last important one is probably inlining, which basically just takes a piece of code and pastes it in. This is going to make your code size grow a lot more. But again, the catch is you have more code spatially within context, so you don't have to guess what function you're jumping into. And oftentimes I've found inlining and unrolling, the combination of those two are probably the best. If I can only pick two optimizations, those are the ones that are going to help your hardware the most. Okay, so anyways, we got a bunch more of these rules here. Like I said, there's other talks here. Yeah, how do compilers optimize code differently for ARM and x86 architectures? Yep, that's a great question, because the ARM and x86 instructions are going to be different, right? So basically, what typically happens if you're using a compiler like GCC or LLVM, typically it'll take your code, compile it into some intermediate representation, and then from that intermediate representation, so again, it's not C++ code, but something that looks assembly-like, but it's not a real assembly language, then I'll take that assembly-like representation and translate it into your target machine, the ARM code or the x86 machine code. Now, during that process, there are in the compilers what they call like the machine optimization pass, basically, which it'll take the intermediate representation and say, okay, I know if I'm targeting x86, this pattern of adding two numbers and then multiplying them, I should use this instruction because that's better. But here's the ARM way of doing it. So there's two sort of separate paths. So that's typically the idea. There'd be two different optimization passes based off of the target platform. The other term that you can look up is called term rewriting, where you'll look at a assembly instruction and try to rewrite it to do the strength reduction or generate something more efficient. But again, that's usually happening at the intermediate representation, and then it'll generate the efficient ARM code or x86 machine code. So that's typically how the optimizing compilers do it. Yeah, and they're pretty good at it these days. these days, maybe a really good programmer like the one I'm highlighting on this slide here, Agner Fog, can hand tune x86 code better than your compiler can produce, but our compilers scale much better. And Agner Fog's a good person to look at their website to understand like optimizations and stuff in code. And I think specifically he looks a lot at x86, although maybe he's been doing more ARM work now. His ARM's much more popular. Yeah, great question. All right, let's see. I got just a little bit more on the bigger patterns that could benefit performance. And this is just an example. I'm just going to run through it in like 2 or 3 minutes, and then I'll wrap it up here. But what if we've got a real problem? Because I've shown you a bunch of sort of micro benchmarks, very very small code snippets. But what if you actually are programming a game, and you have a game character or an object in that game, right? It's going to have a texture, like some collision box for physics, the transformation, so we know where in space we are, maybe some other state, maybe it's got some artificial intelligence, right? I mean, if we put all these components together in one game object, hopefully there's some alarm bells ringing potentially with pointers, because what's a pointer do? Well, pointer means indirection, right? So that might not be good for our cache behavior if we're just like jumping around anywhere in memory. So this sort of structure here has trade-offs. I mean, the trade-off is it's very simple to understand, right? If you're writing a video game or a simulator or something, you could write something like this. It's easy to understand, easy to maintain, so there's nice software engineering trade-offs, but performance-wise, this probably isn't the optimal thing, right? We'd rather like all of our textures to just be like known locations that we can, cache really easily, not pointers to things. So that's kind of the main summary of this bit here, which I'll go through. It says, typically if we structure our objects in this way that aren't what we'd say cache friendly, then again, it makes our code relatively simple. We can just update all of our game objects in a loop. We call update. We update all of these individual components, the texture, the collision, transform, etc. But again, it's not going to be in a very cache-friendly way. So, and this might also encourage other things like coupling of data. For instance, if I've got all my data directly in the game object, then it makes me write code maybe like this, where I check, is something colliding with the floor, and then I look at the graphic system, and then I look at the sound system. It's a lot of coupling in code with systems that maybe shouldn't be talking to each other. And maybe there's even like cognitive overhead for myself trying to remember. I have to be a sound programmer, graphics programmer, physics programmer, all in this one line of code. So anyways, so this is kind of the issue here. So anyways, let me get us to the data-oriented side here. Okay, so this is kind of bad if we just have these monolithic structures, but it could be good in other ways. So I don't want to dismiss that there have been a lot of games written in this style here. But typically what we could do here is sort of break things out, at least for the maintainability, maybe into different components. So this is a specific design pattern here on developing different components, where basically I just have a component here for doing an update, and then I can separate this out to individual components that a object might need. Okay, so I just have my base classes there and derived class, and then I can have something like this for my game object. Now, this is nice, again, from a software engineering perspective. I just carry with the game object the things that I need. But again, we still have this issue of we have a pointer to some unknown structures here. Okay, it's very convenient. In fact, I don't even know if I like a vector of pointers here. I'd probably want a vector of shared pointer or vector of unique pointer in some cases here. But it still makes our code simple, and we've at least reduced the potential size of these game objects and given ourselves some flexibility. Okay, so anyways, this is just an example of creating a game object creating a component and then adding in the component using this pattern here. Very nice. But again, we want this to be sort of a data-oriented system or somewhere where we can get nice performance. So, okay, there's a few more trade-offs we can make in our data structure. But basically, how do we make this data oriented here in a real example? Well, basically, whether I'm using a vector or a map to look up these components here, how does it look like from the memory perspective here? Okay, so here's just a little bit of a bigger example where I have a bunch of game objects, a bunch of textures. I add them into each of the objects, and then, that's our component pattern here. Again, we still have these lookups here where we're iterating through all of our data. So let me get to the visual here, put our performance hats on. Basically, the problem is if I have now all these components, then I have all these individual update loops, which I need to do for the AI component, the texture component, the collision component, and so on. And, is that going to be cache friendly or not? Well, again, I've got these updates here, and I already told you we had pointers with lots of indirection. So here's kind of the visual here that I want to show you just to get to the point here. The problem is, again, we've got our 64-byte cache line. And, if I'm going to access all of these AI components that are in these separate objects here, maybe if we're very, very, very lucky in our game, they just line up nicely here. That means I allocated objects 1 AI, then object 2 AI, object 3 AI, etc. All those components nicely. In practice, that's not really what happens, though. We create one object, we do its AI part, its texture part, collision part, etc. So there's these gaps in memory here. So already we can kind of see anytime I'm accessing one object's components, I'm basically only getting like one part of the cache line. There's going to be a bunch of empty here. And that's going to hold true in the level 2 cache and so on. So, we're not doing very well here in this particular case. So what's the fix? Well, ironically, the fix is to do the simplest possible thing because our hardware wants to be simple. It wants to be simple and predictive and do the simple thing. And that's going to be to just basically put all these components into arrays here. Okay, so just have my AI component in a simple array, colliders for physics in a simple array, any of the object components for rendering, again, in a simple array. And then when I do my update, every component is simply just updated in order with all of our AI stuff, all of our collision and physics, and then all of our rendering. So this is the better thing to do, just using a flat, simple array. And it's simpler too, it's simpler code. So sometimes the more performant thing is a simpler thing versus this complicated map structure and so on. Another component pattern then just needs to hold the index into its AI components, a collider component, etc. But that's all it really needs to hold on to. Right, so this, just storing stuff into a flat array or maybe a vector, because these things might be, resizing on occasion, is going to be much, much, much more data access friendly for our CPUs. Okay, so hopefully that makes sense and a little bit more of a real world example here. So I think I'm going to stop with that one. There's a bunch more in here. As I mentioned, we weren't going to get through everything. But reusing data with a flyweight is another pattern, which I've given some talks on. So anyways, the takeaway from this talk is, performance is our currency. So, we want to pay attention to it. We want to know what hardware we're writing code for so that we can get more done, or at least get more done, or the same amount of work done more efficiently, right? Why wouldn't we want that? Time is important in our lives. We looked at several optimization patterns after understanding our hardware otherwise to figure out how to write efficient code, and of course talked about things like using perf and so on to profile. And yeah, it's worth playing around with some of the small examples to try to write really good code or try to write really bad code too. You can do that as an example as well, just to see and understand the performance of your hardware. Okay. And I think also, if there's another takeaway from this talk, is you could learn a lot more by studying old games. Look at Doom and Quake. They have the source code's open source, and they had to do things efficiently. And those rules haven't really changed. While the hardware's gotten better and we're able to do more on smaller devices, the same principles, many of those same principles of how we compact data structures and structure data and so on, those have stayed the same since the beginning of computers. So definitely learn from them. And in many cases, there's less noise and there's smaller code bases that you can still learn excellent stuff from. All right, so I've got a bunch of other talks here. You can watch some of my talks, but these are the talks from folks who, in many cases, inspired me. And I consider like a very good list of talks on performance. Okay, so you might recognize some of these folks here. All right, so I think that's a great point to sort of wrap up here. And again, just want to thank you again so much for the invitation to speak today at CppAfrica. It's an honor. You're a great and captive audience, and I'm happy to stick around if you had questions or comments otherwise. So thank you. Thank you.
Okay, thank you, Mr. Shah. I think if you have more comments, you can drop it on the chat. Yeah, please. Let's see them. Okay, some people are typing.
Yeah, let's see. So question, when should I optimize for instruction count versus memory access latency? Which usually becomes the bottleneck? Okay, yeah, that's a great question here. I would say one of the most underused or known flags in our compiler is the -S compiler that does optimizations, capital O of S, optimizations for size, the executable. Which usually becomes the bottleneck. I think that becomes a question of what type of application that you're building. So for instance, if you're building on like an embedded device that has very limited memory resources, maybe that's when the executable size of these things can really start to matter, or the libraries that you're bringing in and so on. So maybe you can pay more time for space in those cases where you need your executable delivered in as small as footprint as possible, and then while the actual application's running, then it can unroll and generate some of the data. And a great use case of that again was that 96 kilobyte game, so you can see some of the techniques. So it really depends on what your bottleneck is. If you've got plenty of time to do stuff but very limited on space, then you would make that trade-off, for instance.
Okay, I have a question.
Sure.
Okay, I think I was reading an Intel paper months ago about this. They have some machines that are able to, they call it DDIO. So right now, the modern CPUs that do prefetch to reduce future cache misses, they're trying to, I think it's something that was introduced like maybe years ago, not really that long, right, and not really that old too. That your first write is not written directly to RAM, but it's written to the shared L3 cache, so that the first initial request of the data is not a cache miss. It will definitely be a cache hit, but it's not really supported on like every device. And on that, ask if you actually done any code on such CPUs, and what are some tricks if you have, because I've read about them, but I haven't really experienced them, and I haven't done anything with them yet. I think some people are saying you'd have to train some data, because the memory that the L3 cache will allocate for such data is sometimes dynamic and stuff. So I've not really done any experience on that. If you have any experience with such, have you?
Yeah, I have a little bit of experience with this. I mean, this idea, I think what that paper is getting at is this idea of what's called warming up the cache. So sometimes folks, this is especially common in like, let's say like financial systems, where you would simulate some of the workload that's going to happen before a financial market's going to open, so that you have some data, as you alluded to, that's in like the L2 cache or L3 cache, for instance, so that when it's time to go, you can hit the ground running, so to speak, and start running fast and avoid cache misses. Especially if you've got like known data access patterns. That's another place you can kind of get away with this. The other comment I'll make about this is this sort of like, I mean, the cache itself is very interesting as far as this trade-off, which you mentioned about when do I actually write the data? Because some of the caches, right, you have like, you'll basically, as you make changes to the data, it'll write back data to each of the levels so that it can be saved, or only do that once something's evicted from the cache, right? So there's a whole interesting trade-off there. But I think something that I was thinking about too, as you were asking the question, it's back into this like speculative sort of like execution stuff, and this is something that GPUs I think try to do a lot. This was at least true a few years ago, where basically if you executed on some piece of data, and there was a branch, basically it would just take both paths and execute because it was doing it in parallel in different cores, and then whatever branch ended up being the one that you took, it would use that result. Now there's a question of, and I don't know if in this paper is, if you sort of take two different branches and only need to keep one of the results, can you still keep the cache warm from other like speculative data?
Exactly.
Yeah, so that's interesting. I don't know. That part I don't have an answer for. I'd need to read the paper and see the DDIU stuff. Yeah.
Okay. Thanks. Okay, I should think.
Okay.
Let's see.
Sorry. You mentioned
go ahead.
something about speculative execution, but isn't that very dangerous? For example, maybe you check. Okay. Yeah. Please go ahead.
Yes. So a lot of the hardware, right, just getting rid of or sort of patched, right, when the original like Spectre and Meltdown paper came out, which was probably, I don't know, 8 or 9 years ago at this point. Right, yeah, we uncovered this idea that, hey, if I'm executing on data that shouldn't be known, or, I mean, you can imagine the simple case, like if this condition's true, log in, else don't, and then somebody just takes the other path. That's very, very bad, right? So this is being like mitigated in hardware at the hardware level. So there's still some of this like predictive stuff, and in some domains where it doesn't really matter, like the GPU, where you're not doing any input outputs generally, then it doesn't really matter. Just speculate as much as you want if your goal is to just draw pixels on the screen. But yeah, for the CPU, this is a problem. And people try to exploit any type of speculation to uncover data that shouldn't be visible. So yeah, we have to sort of program around this. Yeah. But some domains you don't care too, if you speculate, right? Again, like I said, if you're just building a piece of hardware that needs to compute something and there's no sensitive data or no security risk, it doesn't really matter. But yeah, most of us on our general purpose machines, we don't want them speculating. Let's see, there's one question about when should I optimize? There's a question about perf. Aside from perf, what are some other tools for Windows? Let's see, I haven't been working on Windows much recently. There was a tool called Very Sleepy, which was an interesting profiler that was freely available. That was one that I had used a while ago. Whatever tools Visual Studio has built in are also usually pretty good. So you could get Microsoft Visual Studio's compilers. There are other tools built into the compilers as well. So like LLVM has things like you can get branch count numbers out of particular pieces of code. Those can also be very useful depending on the type of optimizations you're using. What else is out there? Yeah, those are the ones that immediately come to mind on Windows. You can usually get a profile like out of your compiler. There are interesting things like getting like a flame graph or something out of like GCC or the client compilers if you're using those on Windows, so you can kind of see where you're spending a lot of time, and that'll kind of lead you to where you should spend your time optimizing. Let's see. There's a question about a pattern on the last slide where we updated the components. Yeah, this is exactly the like structure of arrays versus array of structures type of thing. Yep. Yep. So that can be a big trade-off. Let's see if I have it. That's a bit of the component pattern here. I mean, flyweight is one place where we think about this. If this is where you're talking about. Yeah, that's definitely a good optimization. Some compilers, even some other programming languages, allow you to actually just flip, so you can have with like a pragma structure of arrays or array of structs. I can't remember if OpenMP has that, but I know that I think the Odin programming language had something like that built in. If folks have ever taken a look at Odin. Yeah, other questions? Okay, yeah, somebody's commenting on WPA and WPR, Windows Performance Analyzer and Recorder can be useful. Yeah, awesome. Thanks for sharing those. Yeah, I think there's been a lot of. I work on Linux, but I think there's been a lot of awesome stuff. In all the platforms for this. Mac has Xcode and instruments, and oftentimes you'll find small developers building really cool tools. Where it can also get interesting though is if you're working on like distributed systems and stuff. Then monitoring performance and stuff becomes a whole different challenge. But there's probably interesting tools out there that I don't know as much about in that world. But I know folks usually end up building custom tooling for that.
Okay, I want to speak on you mentioned changing from struct of arrays to arrays of arrays of struct to struct of arrays for DoD, data oriented design. I think the new reflection could make people write libraries that could do it automatically, much like how Odin and is it Zig? I think allow you to do it currently.
Yeah.
So I'm excited for that. So I just wanted to point. So that could be.
Yeah, that'll. I think I don't remember if it was Herb Sutter who gave a talk this year at CppCon. He might have used that as one of his examples. I can't remember. This is something that I've done in the D programming language. It's probably an awesome. I'm glad you mentioned that. That'll actually be an awesome thing to try with the reflection. Reflection is going to be a big deal with C++ 26. I'm really excited to play around more with it. I think it just landed in GCC 16.1 for those of you who want to play around with it. Yeah, awesome. I think if there's no more questions, I think there were a lot of awesome questions, and now I'm part of the Discord here, so feel free to ping me, or I'll keep an eye on the other awesome great talks. And again, I just want to thank the organizers for making this an awesome event. This was an awesome way to spend a Saturday for me, and I hope you all enjoy your evenings, and we'll talk again in the future, I'm sure. Thank you.
Thank you. Yeah, you can. Okay, so Mr. Michael, we have right now the slide for today, the talk for today is over. So, but we usually just have a community meetup afterwards where we can discuss, maybe suggest different people that you could invite if you have anybody in mind. Also, people that we could or anything affecting the community at large. So if you want to be part of the discussion, you can stay. But yeah. And thank you for the talk. It was really exciting, and you touched so many areas and showed so many things. Thank you.
Thank you.
Mike, one last question.
Okay, sure. Yeah.
I'm surprised you use Linux for maybe I'm not aware of it, but with what we hear, most people do like GP programming and these like Unreal engines on Windows. So like, why your choice of Linux?
Yeah, it's just the tool stack that I work most efficiently on. I found a lot of our like cloud and a lot of the cloud infrastructure that I've worked on is usually Linux anyways, so it's easy to kind of go there. The GPU stuff, I guess maybe I'm a little bit of a weirder case in that I like been using, I should say, OpenCL more than CUDA. So the driver support there has been okay. Versus with CUDA, it's still pretty good, but I think historically NVIDIA and Linux is maybe something people shy away from. So, but yeah, I'm happy to throw out a few names for folks who might be good speakers. I saw you had Bryce and Connor recently. But Keith Stockdale, who does a lot of game programming, he might be somebody interesting. I think, of course, if you can get like Jason Turner, any of those guys, or Tom Tesh, who was recently on CPP Cast and does game programming, I think he's a great lecturer. I'll put those names in the chat here.
Thanks.
And if there's anybody in the C++ world you want me to just ask too, I'm happy to ask them if I know them. There's a chance I might know them.
Yeah, like, do you know anyone in the embedded system space? Like, I think that's where I kind of personally pitch my tent in.
Oh yeah, let me see here. I'll give you two names right now. I just gotta look them up here. I think, let's see here. And have you guys talked to, let's see. Ben Sachs gives a lot of training. He's given a few CppCon talks, more than a few actually. But he might be someone good. And feel free to mention that I mentioned a name, or I can reach out directly. Maybe Dennis or Emmanuel or whoever, just send me an email and I'll do that.
Thank you. That was nice. All right. Does anyone have anything to add? So we can call it a day.
Yeah.
Oh yeah, Dennis.
All right. Thank you very much. It's been a wonderful year. We've learned a lot. It's a lot anyway. Hopefully we'll be back very soon. Hopefully we'll be back very soon. All right. Thank you. We so much appreciate your effort and time.
Thank you.
All right. Yeah, thank you. So take care, everyone. We would be having the next one next month sometime. We would complete the weekend, but it's usually one of either the third or the fourth Saturday in the month.
All right.
Bye, everyone.
All right. See you guys.
Yeah, see you.
Bye.
All right, thank you, everyone.